so next we're moving on to 2.2, which is the square root of a function. Let's look at the first part of notes here. If f of x represents any function, then g of x equals square root f of x is the square root of the original function. So you guys, what that means is f of x is the original function. What I'm going to do is I'm going to root that original function. So what we mean by that is if you have a function, f of x equals 3 minus 2x, then g of x equals the square root of that original function, 3 minus 2x. Now when we square root an entire function, we're actually square rooting f of x, and f of x is your y values. So we're actually going to square root all of our y values to get our new square root function. Alright, so we're going to graph this using a table of values. To do that, we'll take our x's, and we'll do -2, -1, 0, 1, and 2. And then we'll find the matching y values for the function 3 minus 2x. So once we have our table of values, we see that it's a linear function, and we're going to graph that line on the grid. Now for the next part, we're going to take the root of 3 minus 2x, which means we're rooting the y values. So we're going to start with the square root of 7, and the square root of 7 equals approximately 2.65. You guys, those little wiggly equal signs means approximately or equals approximately. If I square root the 5, we get it equals approximately 2.24. If I root 3, equals approximately 1.73. Square root of 1 is 1. And the square root of -1 is undefined because you can't square root a negative value. So now let's plot this on our graph. Okay, there's one more point on this graph that is very important. And the other very important point would be on the original line, your x-intercept. Now in this case, your x-intercept happens at 1.5. If you plug in 1.5, you get an x value of 0. Now this is also an important point because when you square root 0, you get 0. So at 1.5, your new graph is also an x-intercept. So that's going to be another very important point. Now something we really need to pay attention to, again, this is making that same radical shape we talked about last day, but something you need to pay attention to is that your points connect from 0 to 1, and here your new graph is going to be over top of the original graph. For the rest of it, your original graph is going to be underneath, or your new graph is going to be underneath the original graph. That's because if you square root a y value, let's say the y value of half. If you square root half, the value actually gets bigger. So when you square root a small number, again, it gets bigger than it was before. So this section of the graph is going to be on top of your original graph. That's going to be very important, and on your test, it does need to look like that in that section. So in this next part, I'd like you just to write some of these notes in, please. This is talking about the relationship between a function and the square root, and it's just a summary. So first of all, this is saying that your y value is less than 0. So in other words, it is a negative y value. If your y value is negative, your root function is going to be undefined, because again, we can't root a negative number. If your y value equals 0, okay, if your y value equals 0, the square root of 0 is still 0, right? So this would be your x-intercept. It's also an invariant point. So we're going to write underneath, this is an invariant point. Because when you root 0, it's still 0. So that's an invariant point. Next, we're going to say our y value is between 0 and 1. So if y is between 0 and 1 and you root it, your y values get bigger, which means it's going to be above the graph. The example of that we just did was that root of 0.3 equaled 5.48 or something, okay? So they get bigger as you root a small number.
We don't have room above that.
That's okay. Here you can write y equals 1. because that's really what it's saying here is that y equals 1, and when you square root 1, it's still 1, so that's another invariant point.
Or just remember fx is 1.
Yeah, f of x is y. Here we're saying that our y values are greater than 1. So the last one here is saying that our y values are greater than 1. So when we root these y values, when you root a big number, it's going to get smaller. So anytime you root a big number, it's going to appear below the original graph. So again, if you compare 2 points right here, the original point is higher up. When you root it, it's going to be smaller. So let's look then, our red graph here is f of x. Let's think of our domain. Again, this is a parabola. So the domain of the parabola is everywhere, so we say that x is an element of reals. The range for the parabola starts at 2 and goes down from 2. So we say that the range is y is less than or equal to 2. There's two x-intercepts. One is at 2 and one is at negative 2. The y-intercept is also at positive 2. Now when we say the maximum, we're talking about how high does it go as a y value. What's the highest y value? 2. And how about the lowest y value of the parabola? Right? There is no low. It goes on forever. So you could say none. Or you could say negative infinity. Like it goes down forever. But none is also appropriate. There's no minimum. Now let's compare those to that of the green graph or the rooted function. So when I look here at my domain is not anymore an element of the reals, because the domain stops at negative 2 and goes up to positive 2. So here we say that the domain now is only between negative 2 and positive 2. Again, that's because it can't go in the negatives, so it stops when your original graph would go into the negatives.
What's the negative 2 with x?
Okay, let's keep going. So the range of this one, now I'm thinking about my y values. The smallest y value is 0, and it goes up to a y value of root 2. So we would say that our range is between 0 and square root of 2. Again, notice that your other range was 2, but when I root my y values, that 2 now becomes a root 2. The x-intercepts are the same. They're still negative 2 and positive 2. But my y-intercept, again, is different because my y values are rooted, so my y-intercept is going to be root 2.
Why don't you just put 1 point?
You can. You could put 1.41, but it's only approximate. 1.41 is an estimation because you had to round it. So square root 2 is more accurate. Let's go then the maximum value. Again, it's no longer at 2. That value was rooted, so it's at root 2. And the minimum value, there is a minimum. It's 0, right. You can't go into the negatives, so all of these rooted graphs stop at 0. All right, this is example 2, so I'd like you to try filling out this table on your own. Again, notice here that your blue graph has a y-intercept of 5, so the purple graph has a y-intercept of root 5. So please just check your answers with those on the board, and we'll move on to our next example. All right, example 3, what we're doing here is we're given a graph, and we're now going to graph the corresponding root function. So I'm graphing the f of x values under the root, which means I root the y values. So you can write yourself a little note. We're going to root the y values. Okay, I'm going to also choose a different color. When I do this, I have 2 steps. Step 1 is always plot the invariant points. And that's because you guys know they haven't changed. So those are the easiest ones. Remember, the invariant points are where y equals 1 and where y equals 0. So on this graph, you start at a y value of 1, and then you go over and see where that meets up with your graph, and that point is going to be invariant. Then you go to a y value of 0. You go over to where that meets your graph and plot that point. That's also going to be invariant. So right away, plot your invariant points. Then, step 2, I always think this sounds funny, but then you're going to plot more points. Okay? When you plot more points, some good points to pick are often y-intercepts. The y-intercept is usually a good one to pick. Or other nice points. What are nice values to root, you guys?
1, 4, 6,
4,
9.
9, right? Nice, perfect squares. Good. So when I look at this one, I see that my y-intercept was at 4. Where would it be now that I rooted it? 2, right. There's another point over here that would be at 9. When I root it, what would it end up at? 3. A little off there, but it would be something like this. Now the final thing you have to make sure is between your invariant points, you need to connect the dots above your original graph, and then the rest of your graph will end up being below your original graph. All right, our final graph for today, we follow the same steps. Step 1, plot your invariant points. How many invariant points are there going to be on this graph? 4. There's going to be 4, right? Because if you look at y equals 1, the parabola hits y equals 1 over there and over here. Then if we look at y equals 0 over at this side and over on this side.
Oh, it's the same graph.
Now let's plot more points. So for example, if I look at a value of 4 and I root 4, I get 2. So 4 becomes 2 right about there. On the other side, 4 becomes 2 right about there. 4 becomes 2 right about there. Now in between my two x-intercepts, your original graph is down here in the negatives. You can't root a negative, so there's going to be no graph in the middle of these points because you can't root a negative. So it's going to go to the outsides of each part. So it's going to look something like that. Again, the middle is undefined when you root it because it's negative values. So there's going to be no middle section. And if you keep rooting numbers, like your 9 becomes a 3, here your 9 becomes a 3. It should be a little taller than it is. Okay, but it should look a little bit more like that.